Day 35, page 790, problem 12. This is what they sometimes call in math, I believe, a step function. There's three distinct parts to this problem. There would be a little bit of a transition from each part to the other. We're going to ignore that. For example, from 0 to 0.3 seconds, there's going to be an induced voltage because the rate of change of the magnetic field is different than from 0.3 to 0.4 and from 0.4 to 0.5. All right, so once again, when you're inducing voltage, there has to be something changing. In this case, the magnetic field is changing. That's the most common thing. And you have a 10-turn coil. And the nice thing in this problem as well is the units are all set. You know, meter squared, Teslas, seconds. So we can figure out the induced voltage from, well, like I say, three phases here. From 0 to 0.3 seconds. That's one induced voltage. And in this case, I'll maintain the negative. You'll see what happens here. What changes is B. N is not changing, it's 10, but you have a negative, basically 10. The change in B, 10 is the N, but the delta B here is a gain of 0.3. Starts at 0 and goes to 0.3. So the delta B is 0.3 Teslas. And the area is given as what, 0.25? All right, so and our time frame there is 0.3 seconds. That's kind of nice mathematically, because if you do the math there, that comes out to be, well, the 0.3 is canceled. 10 times 0.25 is 2.5. Let's call that negative 2.5 volts, joules per coulomb. So that's our first induced voltage as a function of the time from 0 to 0.3. It's constant at negative 0.25. It's constant rate of change of the magnetic flux. Now, from 0.3 seconds to 0.4 seconds, nothing's changing. There's no flux change. Nothing else is indicated that's changing. So there will be a zero potential difference, zero induced voltage over that time frame. But now, from 0.4 to 0.5 seconds, there is an induced voltage once again because there's a change in the magnetic flux. And it's once again, we're going to go negative, 10 turns still, 10 turns. The delta B is negative 0.3. It goes from 0.3 to 0, so that's a negative 0.3 change times the 0.25 meters squared coil divided by a time of 0.1 seconds. So over that time frame, if you do the math there, you get positive 7.5 volts. So those are your three answers. You have negative 0.25 volts during the first part, 0 volt induced voltage in the second part, and a positive 7.5. The positive 7.5 just being, bottom line, is going to cause a current in the opposite direction as the negative 2.5. So if the negative 2.5 volts was a clockwise current in a coil that you had laying on a table, the 7.5 would induce a current, if you knew the resistance, in the counterclockwise. If I said clockwise in the first case, it would be counterclockwise now. So there's where the negative would be appropriate or applied when you have a known loop with a given direction.